Here we are, hold down. It is the simplest of things. I think I mentioned it last week and over the course of all trainings. If we can't hold it, we can't cut it. That is, very, very straightforward and, kind of easy to understand. But the one thing that is missed is if we are not holding it well, we are not getting or not going to get a good cut. So it's your quality of hold down is really a direct relation to the quality of the edge that you're going to get on your material. So here are certain types of hold downs that are possible. Only a few of them that are listed. There are many, many others. The one that I used a couple weeks ago that is not on this list is a hot glue. It's a method I used to use several years ago for holding parts in place. It works well. It depends on what your material surface is. What I used hot glue just the other day, the glue was a little too strong. So when I pulled it off the table, the glue actually pulled off some of the spoil board or left some pretty good divots in the table. So there is different qualities of glue or strengths of hot glue. So, basic screws, nylon nails, double-sided tape of all varieties, spray adhesive, that's like a 3M77, clamps and vacuum. And we'll take a look in depth at a little bit of each one of these here as far as pros and cons to the process here. So, the pros are, it is held securely. And it's very quick and easy to just, run some screws in there. The challenge of it, even though they do hold and they're held securely, it is not holding your actual part unless you, plan in a path that you might have some holes already in your part that you're able to stop the machining and place some parts and some holes in there for screws. So even though screws is a very secure method of holding it down, it still may not be good enough for some materials. Again, mainly because of the scrap, or in this case, this preview that we have here, we have a screw 1, 2, 3, 4, and 5 locations. It is not holding anything in this area here. So if we're using an upcut spiral bit, that material could kind of vibrate and bounce around there a little bit and cause some quality issues or edge quality issues. You do have to watch the cutter path in where the cut goes, so you don't want to hit a screw in the middle of cutting. So what is visible here in this preview is I've actually drawn out circles of where it is safe to put a screw and use the machine to just barely touch the surface, just 1/16 of an inch or so, just enough to mark the surface. So at that point, there is no hold down holding the material in. It's just weight and gravity holding it there. But that's okay because it's a straight down, straight up, and just barely touching that surface. And that then allows you to know exactly where the screw is in your cam software to know that it is not in the middle of the cutting path. The other, two big disadvantages that I don't like about screws, but generally that's what I do here at home and out in the garage is, screwing it down. It does leave a lot of holes in the table. So much so that you go to screw another board down and you just run into the same hole that was already there. So the more of those holes kind of gets stripped out, the less it's going to hold into the material. And the biggest one that is an aggravation is a broken screw. As you go in and drill this in, you will possibly make a, break a screw as it is, as it's cutting. So you don't want to have that happen because then, you really mess up your table trying to get the board off. So that is screws, nylon nails. This is one that a lot of people use. I don't like it. A couple reasons. One is I have not had luck with these nails really
No.
going through all the way and holding boards in place. And they just kind of bend and kind of compress as they cut in and don't penetrate into the table surface as much as you might think. But if you are cutting material that is suitable for the strength nail to hold it down, it's very nice. It holds the boards securely in place. It's very quick and easy. I mean, just air, not a problem. And then it doesn't damage a bit if you do end up putting a nail in the path of the cutter. The cutters are able to just go straight through these without any issue. Another advantage to this is removing it. Even though I have removing on the cons side, sometimes removing is an issue, but if we use the same method as I showed with the screws by using the CAM software, the CAD software to place those holes, you know, and to know exactly where it's okay to put a nail, you could then, after you're all the way done cutting, use the machine in those same hole locations where you put that nail to do a drilling tool path that goes all the way through. And basically you're just drilling that nail completely out. The one thing that I don't like about the nylon nails is when you do remove them, sometimes they snap off in the table, which is okay, but then you know, I end up brushing my hand across the table quite often to, you know, remove some dust, and yeah, you're gonna bleed yourself a little bit if you run your hand across one of those broken nails. So just be cautious of that. The clamps is another method here. If you have a desktop machine with some T-slots, you're able to, you know, clamp them down and hold it off on the side. That is a great method. To hold it down, one disadvantage of this is it is not holding anything down as far as the scrap or the center part down here. So if you are cutting with a up spiral bit, you can and may get some vibration and part lifting up off of the table. And again, that part lifting and that vibration is going to affect the quality of the cut. You do have to watch the cutter path. Mainly, it is off to the side, so X and Y generally fairly safe with that because you're not going to necessarily cut that close to the edge. But your Z level, make sure that your Z is up high enough to clear any clamp that you may have on the table. And a big con, like I just mentioned, is only able to cut the perimeter of the, hold the perimeter of the part and nothing on the interior of the part. Double-sided tape. This is one that if you've been sitting in on the Wednesday classes, this is one that I also use. Between double-sided tape and screws are my two biggest methods of holding parts in place. The you know, the pros is it's holding everything. It's the scrap and the part itself. It's fairly quick, easy to use. The cutter path isn't really an issue, although when you do cut through, you know, double-sided tape, it does kind of make a mess of the bits a little bit and kind of gums up the cutter. So that is on the con side. And you can't really confirm the hold down. So if you have it taped down and your full sheet is there and you press it down and you push it, it feels like it's held down. It's not moving, but as you start cutting the parts out, you then realize like, oh, well, the board was cupped a little bit and it was only stuck on the outside and not on the interior of that part. So that is definitely an issue. There is also an issue with cutting in double-sided tape of cutting on top of Jello. You have to be careful not to get the tape that is too thick that you might think is a good idea to compensate for flatness and such. But once you get too thick, that tape could vibrate and kind of wiggle and jiggle, which is going to show up in the quality of the cut as well. The spray adhesive, I haven't used that for a while. I was there for a while. It was like my only method of holding parts in place. I stopped using it mainly because it makes a mess of the surrounding area, the overspray and everything else. And you also have to be very careful if you're holding, cutting aluminum or product that is able to dissipate heat. Even though you start out with it being held down very good, solid, as you're cutting, the aluminum is going to heat up as it's dissipating the heat from the cut, which is going to start releasing the hold down method of that spray adhesive. So vacuum, there's a couple different types of vacuum that you can have. One is a low pressure, high volume, and then there's a high pressure, low volume. And what we're talking about with pressure is the weight of the atmosphere, the weight of air. And volume is the amount of flow, how much air are we pulling through. So generally with vacuum is, just your shop vac. When you have turned it on and the hose is not plugged up, air is just getting, pulled into that vacuum, sucked in there, that is a high volume. And at that rate, it is going to be low pressure because you have no pressure building up there. But as soon as you plug off the end of your shop vac hose, you hear the motor starting to work a little bit. That is building up pressure. So generally, you will have high pressure when you have no flow. And when you have no pressure, you will have a volume of air flowing through it. I'm not going to, you could watch the video of this and just kind of dig into it a little bit. Just understand one thing that we'll talk about here a little bit is what is the pressure and what is, perfect vacuum, and what is it that you want to be able to achieve with this. Perfect vacuum is the 29.21. You're never going to get a vacuum that is any better than that unless you have your vacuum inside of a pressure chamber that is able to increase the atmospheric pressure. So that is also at sea level. And basically divide that number by 2, is it going to get your pounds per square inch. And what that is a column of air. So 1 square column of air from sitting at sea level all the way up to the outer atmosphere, that column of air is going to weigh 14.7 pounds in that inch. So you could kind of multiply that over a 4x8 table, and you're going to find out that you have you could have a couple tons of weight of air pulling down on your material. Oh, we have a low pressure, high volume system. This is generally like a regenerative blower, shop vac type system where they are not able to really produce a lot of pressure, but they just move a tremendous amount of air. And that air that is flowing through here is able to compensate for the lack of pressure. So the reason I'm pausing just a little bit here is I'm looking for a calculator just to do a little bit of math. So I'm saying this system is good for a cabinet maker. So if you're cutting 4x8 sheet of plywood, that is a total of 4,608 square inches. A good shop vac, or not even a decent shop vac, is going to be able to get you roughly 5 inches of pressure. So you're going to end up getting about 2.5 pounds per square inch. So that means if we multiply that 2.5 times that square inches, we have 11,000 pounds of air sitting down on top of that plywood. So even though it's just a small little shop vac, That's a lot of weight that we're applying to the top of our material or top of the 4x8 sheet, which will hold parts in place. Now you do have to be concerned about as you cut all the way through and you start opening up leaks, now we don't have that pressure anymore, and we're going to look at strategies to be able to overcome that. So then we have systems that are a high pressure, low volume. And this same type of system, this is generally like a rotary vane type pump. And the rotary vanes, they range in price. Down as low as 500, that's able to get 25 inches of mercury. At 500, but you're going to have very low CFM. So you have to use like gasketed material. You have to prevent leaks in the system and prevent cutting inside of where you have the gasketed parts off. But then we also have, and there is also the larger horsepower rotary vane pumps, like the larger Becker pump, where that is also high pressure, where you're getting, it's able to achieve, 25 inches, but we are also up at 150, 200 CFM. So that's like the best of both worlds. But the higher the volume, the higher the pressure, the higher the price. So a good solid, rotary vane, Becker pump, I believe costs like around $7,000. So there is some of that, but very, very nice pump to use. So with the vacuum, pros is it is going to hold it securely and evenly. That is really the most important part, and the biggest advantage of vacuum is it is holding material and your scrap and the whole sheet just evenly. So the hold down is consistent across it, which is going to really show up and give you a good quality cut. After I get through this, I'll mention personal experience failure that I had that demonstrates the pros or the security of the vacuum. It's very quick and easy. Just throw your sheet up there, turn the vacuum on, it's held in place. And like I said, it could hold the scrap part, because holding the scrap, and a lot of people tend to forget this or not completely understand it, is it's just as important to hold your scrap material as it is to hold the part that you're actually cutting. Because if you don't worry about holding the scrap is going to be bouncing and vibrating around on the outside of your part, which is vibrating and bouncing into the cutter, which is going to then resonate into the part that you actually are cutting and that you're most concerned about holding down. So holding scrap down is very important to remember to do. And it's also very important to always look at and compare your scrap part to your finished part and make sure that you're not throwing your better edge away. So typically you will have a better looking edge on scrap parts versus your finished part. And that's different topic, but that is select incline versus conventional. So pay attention to that as well. The cons is you just don't know if it's holding. As you cut all the way through, it feels like you're solid. As we just did that math, we could have 11,000 pounds sitting on top of here, but as we cut through, we are going to start reducing that pressure as we open up leaks. So you're never going to be 100% certain that the vacuum is holding your parts in place, or the finished parts, even though for that, but again, there's strategies for that versus with onion skinning, path, plunge points, and start points of where it's going to cut and cutting direction and such. So I'm going to look at that here, and that is kind of about it on the PowerPoint side of things. But the best method, there really isn't a best method. It's all of them. There isn't one that is necessarily better than the other. Certain applications, yes, one might be better than the other, but in some cases, I've used vacuum and screws. I've used vacuum and carpet tape. I've used screws and carpet tape, so it's a combination of screws. So just because we went through each method doesn't mean you have to use each method separately. You can combine them, and you might have to combine them to make them one item. So now we're going to take a look a little bit at some strategy in cutting. So this is kind of a typical nesting of some cabinet parts. And the idea when working with vacuum to be able to get the most out of the vacuum is want to think about where the plunge points are and what direction the cutter is coming from, and really want to start with the smaller parts first. So with this scenario here, in cutting order. So again, looking at this, I would probably cut 1, 2, cutting them in this order. So yeah, there's 1, 2, 3, 4, 5. Now these parts here are 6, 7, 8, and 9. So we have ways within Vectric to be able to say, I want to cut these parts out in the order that I have selected to maybe clarify or help take out some of these noise. I'm just going to select all of the internal features and remove them because we're really only talking about hold down and methods for being able to perimeter cut without a vacuum. So I'm just removed everything that was internal and only going to focus on a profiling toolpath on the outside of the selected lines. So normally we don't worry too much about where the start points are or where end points are. Well, we should worry about what direction they are, but the part order don't necessarily spend a lot of time with that. So typical, just select everything, coming up into the profile toolpath, giving it a depth to cut to, and then specifying a cutter, which I don't fully have my database set up yet. Well, I'm going to, let's put a new tool in here. So I want a end mill because I need to do it anyway. So bonus, learn and see how to enter in a tool, although I'm not going to speak too much of the settings here. We could see that as you move along. And I'm setting, just to mention, I have the material set to softwood, which would be like a plywood. So I'm entering in the numbers here and the values that I would use for cutting plywood. Oh, look at that, I messed up. So I'm going to select that again. It is in there. It is not a 3/16 inch bit. I want to edit that and change that to 3/8. So the description is actually matching what it is. So cutting on the outside, I'm not going to worry too much about any of this just yet. Just going to come down and hit calculate and see how the path looks. So yeah, sorry, I should have mentioned this. There was a question about the vacuum hold down being able to bleed through a MDF is a porous material. The first time I set up a machine, and it was my own machine, and following through the directions, told me to, cut some holes in this table, which you could see here. And then it tells you to go ahead and cut a grid pattern, kind of like a waffle iron thing. It was all great. Everything, I'm understanding what's going on. There's some separation. within zones. And then like the next step said, cover this up with a sheet of MDF. And I thought, I'm like, well, why did I spend all this time cutting all these grooves and putting all these holes if I'm just going to cover it up with MDF? I didn't believe it. I actually called ShopBot. This is, 15, 18 years ago, and said, why do you want me to cover up all this hard work that I just did? And they kind of had to explain to me that, no, it's porous. It'll bleed through that. I'm like, all right, well, go for it. I'll try it. And sure enough, it did. And at that time, I was just using a shop vac. So even a small shop vac machine or powered machine is still strong enough to bleed through and pull through MDF. So yes, definitely can be done, and that's the way it is done. And actually cutting on top of a waffle iron grid like this actually hurts you in a vacuum. A lot of people think that you end up getting a better hold down if you just threw your board right down on top of this. But then when you go to cut all the way through, you cut into that grid a little bit. Well, you could always fix that. But what that really does is allows more of a leak and more of a direct flow, and not be able to build up an even pressure across the table. Like you lose all the vacuum and all the airflow through that one little spot there. So yeah, definitely bleeds it through the MDF. So I'm going to take a look and rotate this around and follow how the cutting is. Well, it kind of looks like it's cutting in a decent pattern that I would already want. So this was an imported drawing. So from another software that looks like it did a decent job of putting the start points and everything right where they would be, except for this one right here. I don't like the location of that. So I'm going to explain what I'm talking about here. So coming over to the 2D view, I'm going to uncheck this. I'm going to look at the strategy or the path here. So if I select everything and type the letter N, node editing is turned on. And actually, it's not good at all. So we are cutting in a conventional direction. And we could see that by what this arrow is pointing right here. That is, oh, I lied. That's a climb direction, which is not good for plywood. So I'm going to double click the profile here and change the direction to conventional. Select recalculate, and again, coming over here to the 2D view, the arrows here are showing the direction of the cutter. So it's going from left to right around the outside of this part. Now, imagine if we're cutting this part, we have hold down, this, solid hold down across this whole sheet, as we, hopefully just learned or remember. There's a lot of weight sitting on top of this board. But now if we start the cutting right here at the lower left and work its way as it's cutting up, over, and when it gets right here to this point, we still have some cutting to do from this point down. Well, now at this point, there is nothing holding. We've like completely disconnected this part from the rest of the sheet. So very strong possibility that this part is going to shift as it's making a 3/4 inch single pass down through this area here. Vacuum will probably not hold that part in place by itself. But now if we change the start point from this lower left corner and moved it to the top left, we will probably be all right with this one, because now I'm going to node edit this one here. So as it's cutting here, over, up, and as it's coming across here, this part is still connected to the larger part of the material, so it can't move. The only time that it could possibly move is when it makes this final connection back to the start point. And what would happen is it's not going to get kicked off the table. It's not going to go flying across the shop. It just kind of gets a little bit of a shift, bounces off of a little bit, which may end up leaving a little bit of a radiused end right there, but we're moving fairly quickly through this material. So even if it does kick off to the side a little bit, it's probably not doing any great damage to the part. If anything, we're leaving a little bit extra material there that could be sanded off. So just going to go through a couple of these other parts, selecting them individually one by one and changing the start point. And I'm changing the start point by hovering my mouse over top of where I would like to have that start point be and select the letter P. I'm going to go through the process of this kind of in the order that I would want to have them cut. And I know it was the letter P for that start point simply because right-clicking and saying make start point, and you see this letter P right there. So that is saying that that is a shortcut to that letter or to that command. So knowing the shortcuts really are going to speed this up a little bit. Now this part here, even though so far I've been going to the upper left, this part I'm going to go to this lower left point right there. And same scenario, it's starting here, working its way around, up, over, and as it's coming down here, it's not completely releasing its hold down or its attachment to the rest of the sheet, which still has a very solid amount of surface that that vacuum is holding in place. So we're probably good with that one. And again, just coming down here, changing the start points on these parts. And again, well, look at that. That one's already right where I would want it because it's going to come across, up, over, and down. While this last part really doesn't matter. It's probably just as fine there as it is over here because, you know, it's everything is already removed from it. But I will change it to the lower right only because this part is at the lower left. So it's up, over, down, and saves the machine from a little extra travel, which is going to be a little bit more efficient on your cutting speeds and getting the job done. So now with the start points changed, I'm going to take a look at the features or the settings within the profile toolpath itself. So I'm going to double click. I'm going to deselect simply by clicking off of all parts. And I'm going to take a look at some of what we have. First, you will want to have the show advanced features checked because these what we see is only going to be available with the advanced features, and that gives us a secondary tab or another tab down here. I'm going to look at the start at, and first we want to keep the current start points. So all of those points that we just made, that's what I want to have. The order, I'm going to uncheck everything here and check the box. It says vector selection order. So that means that whatever part I click on first or select first is going to get cut first. So as I'm not going to do a sweep select, holding the shift key down, selecting the parts in the order that I would like to have them cut. With that complete, selecting calculate, we can now see that the plunge points are right where we set them, and the pattern of cutting is going in the order that we have selected the parts. So even if you don't have a large vacuum system, I would very confidently be able to cut this sheet of plywood by going through the strategy that we just did. I would very confidently be able to hold those down with a basic, shop vac from, one of the hardware stores. You will eventually burn up that shop vac because, the vacuums, that type of vacuum is not designed to have airflow completely blocked off. but for 50 bucks, you know, you could really set up a nice vacuum table, and yeah, that 50 bucks shop vac may only last you 1-2 months, maybe 3 months for the price. It's an awesome hold down, and you will be able to hold them down in place with something like we just showed. And that's all cutting in a single pass without any issue. Now, there is a case where that last part that we cut, if you are at all concerned about, you know, this part being held down with the vacuum, where these two parts alone, I am certain would be strong enough, a shop vac style vacuum table would be strong enough to hold that down. This is where we could add the advantage or the strategy of onion skinning. So far through all of these parts that we just cut, we cut at a full depth all the way through. Should really be at 0.76 or 0.77 there. This time, I'm going to deselect these two parts right here. And come down and calculate. So they are still cutting in the same strategy in the start points there, but now I'm leaving this open here to be able to take a different strategy on these last two parts, because if you are concerned, you're like, yeah, no, I've seen this part slide and move around a little bit, so I want a little bit more surface area. The strategy we're going to use here is a combination of what we just did, still going with those start points, keeping where they are, and also the cutting order. So this one first, then this one. I'm going to do a profile toolpath. This time I'm going to go almost all the way through. Not going to go all the way through, but almost. So let's go 0.73 there. Still 3/8 cutter. I'm just going to do that in a single pass on the outside and come straight down to the bottom, making sure that our keep start points is there and our vector selection order is good. Selecting calculate. So I'm going to preview what this looks like. So you can see all of these parts here are cut all the way through, but these ones are not. So since we did not cut all the way through, we still have a very solid vacuum hold down across the surface of both of these parts. Now what I would do is make a duplicate of that toolpath. This one right here is cutting those two. Go right click and duplicate, modifying only that toolpath. And this time I'm going to say, I am going to cut all the way through at 0.77. Same bit, still a single pass all the way through, cutting on the outside, same strategy as before, and selecting calculate. So now what that is done is we've removed most of the material with that first pass and left just that thin material there that's still keeping the vacuum underneath of both of these parts. Then we come through and remove that onion skin, which at this point now there's very little force being applied to our parts. So the hold down does not have to be as strong. And removing just, we left, you know, a 32nd of an inch or 1/16 of an inch of material there to cut through, and gravity alone or the weight of those parts may even be enough to hold it in place. So it really wouldn't take a tremendous amount of hold down to be removing just a 1/16 inch, that onion skin of the plywood. Could do that same method across the whole sheet if you really were concerned about doing that. So we could just double click and remove or delete, not all, delete that one and delete this one. So now we're still back to this one, double clicking the toolpath, selecting the other two parts. I'm going to change the pass depth to this to be 0.73. We'll calculate. I'll reset, so we cut this completely out. Well, completely around, almost all the way through, leaving an onion skin. And then we'll make a duplicate copy of that part, modifying this one to cut this time all the way through to remove that onion skin and select calculate. So it will cut almost all the way through with the first toolpath that we created. Then the second one will come through and remove that onion skinning. So I did want to talk just a little bit about like nesting and what nesting is. Nesting is, optimizing parts to be able to fit as many parts on one sheet of material as possible. Now there's videos on this. We're not going to get into any big discussion on it now. Maybe another session specifically on nesting, but I believe nesting is just a fairly straightforward one. But one thing I do want to mention is computers are not the best at thinking. They do not think. They only do what we ask them to do. And for the most part, if you had time to spend and manually put these parts in place, you would most likely, as a human, be able to lay the parts out with far less waste than what a computer is going to be able to do for you. But what is going to happen, it's going to take you a lot longer to be able to nest those in place than what the computer would be able to do. So a few weeks ago, a month ago or so, I posted this project up on a Facebook group. You may have seen it. It's a little penny puzzle that is a kind of the way nesting and the way I think nesting could work. So the idea of this puzzle is you have a pocketed out square of material, and you have a total of 10 pennies. 9 pennies easily fit within this area. The goal to this puzzle is to be able to get all 10 of these pennies to fit within this rectangle here. And I'm showing this because I think this is a good example to show how and why computers may not be able to nest as well as we can. So it is possible. I won't give the project away, but it is, or the solution away. It's not here, but it's definitely possible. I've done it. But again, it's a pretty good example. I can't remember exactly what Facebook, one of the Shop Up Facebooks, it's up there. So a basic penny, I believe, I just had to recreate it because I couldn't find my original one, but I believe a penny is 3/4 of an inch in diameter. Then the outer square that I have here is 0.26. So I'm going to attempt to have the computer nest this. So what we're going to do is go select what is the penny, and coming over to the nesting, offset and layouts under nesting. I've already done this once, so I've made the number of copies. I selected the penny and told it that I want 10 of these pieces. I'm also telling it that I want it to fit within this vector here. And I've done so by setting this checkbox right here. So it is going to attempt to nest or place 10 of these pennies within this square right here. And we could do so, just preview what this is going to look like. It only fit 9 and put 1 off on another sheet. And even if you look up here, I've got everything set to 0. Or pretty much 0. Let's try it down to just 1/1000th of an inch, see if that changes anything. It's still, the computer just can't figure out or just can't optimize getting all the 10 pennies within that little rectangle there. If you, again, I'm not going to give away the solution because some of you may want to cut this puzzle and give it a go and experiment yourself. You can go through and even solve the puzzle yourself by just making duplicate copies of this and moving it around. But you'll have to kind of take my word at it until you solve it yourself, that it is possible to spend some time and to get all 10 pennies to fit within that rectangle with them being laid out right. I just think that's a good example of the difference between what we as humans can do and what computer nesting is capable of. The computer is going to certainly do that a lot faster than we can. You could spend easily a half an hour trying to solve this puzzle, where in just, you know, a fraction of a second, the computer did it for us. So there's trade-offs there. But that is it for today, and hope you all have a good week, and we may see some of you tomorrow. Again, that's tomorrow at 1 o'clock. Have a good day.